do that, and it will hopefully still come. But let me remind you that Nordida is now in Stockholm. Canada at the time for CERN was in fact Copenhagen, which was one of the leading centers for nuclear physics, of course, at the time. But Copenhagen lost in favor of CERN, and so as a compensative measure, Niels Bohr introduced the Institute Nordita. The A in the Nordita stands not for astrophysics, but for atomic physics. But over the years, the atomic physics has become less of a marketing issue and has then been replaced by just a name. So Nordita now just stands for what it is, the name Nordita. And the A has no meaning. But the main purpose of founding Nordita back then was, of course, to foster research in the Nordic countries, which includes Denmark, Finland, Iceland, Norway, and Sweden. Indeed, many of the high-energy and astroparticle physicists that are in the Nordic countries, and most notably in Finland nowadays, really received their initial training mostly through Jerry Brown, who was a professor at Nordita on two different occasions between 1960, or around 1960, and then again between 1984 and 86. At the time, Nordita was the only place which was able to or which have postdocs in the sense that we know it nowadays. But now, in the meantime, Nordita has changed significantly. It has still a vast postdoc program, typically around 12 to 13 postdocs. At any given time, 6 assistant professors for 5 years duration, on the order of 4 visitors all the time, 6 PhD students at the moment, of which 4 are in our group and are sitting here in the audience. We have an administrative staff of 8 people, and altogether around 45 people, after we moved from Copenhagen to Stockholm. We run on a budget of about 20 million Swedish krona every year. And in addition, there is another 4.4 billion Swedish krona per year currently coming from this ERC grant, which I'm holding on astrophysical dynamos. And that's, of course, one of the reasons why we can have such a meeting here. The Nordita runs typically on the order of 8 conferences each year. These are short conferences, sometimes for a fraction of a week, sometimes for an entire week, or even longer. We typically have 1 or 2 schools each year, and Nordita is running between 8 and 9 programs each year. One program lasts for about 1 month. So we are constantly booked out, and that is of course also the reason why most of the time the apartments are taken, and during this week, during the Nordita Fest, the apartments are all free. Nordita is also running a Nordita Masterclass, which is hopefully being restarted again. It will run every 2nd year. That's an interesting way of attracting younger students to Nordita or to research in the future. Nordita also has an active research program of about publishing around 100 papers each year. But one of the many visitors to Nordita is Karl-Heinz, and this is of course one of the reasons that we are running this program, or this conference, in Karl-Heinz's honor here at Nordita. I'm happy to say that I'm maintaining a very active research collaboration with Karl-Heinz. This meeting is dedicated to the alpha effect and beyond. That includes other effects, such as, for example, the gamma effect, turbulent pumping that is, or the delta effect, sometimes called by Paul Roberts, who introduced the name radar effect. It's an effect that is proportional to the cross product of the angular velocity in a rotating system and the current density. There's also a number of other effects which all contribute to the electromotive force. One of them is due to Yoshizawa. It's proportional to the mean vorticity. And then there's another effect which Karl-Heinz came across just recently, which is even proportional to the velocity itself in a system that is violating Galilean invariance, obviously, but such systems do exist frequently. But Karl-Heinz is also working a lot on what is known as the second-order correlation approximation, or SOCA for short. And I would like to emphasize that it's not just that it's applicable to low magnetic Reynolds numbers, but it's more important to say that it's actually accurate, exact, at low magnetic Reynolds numbers. And therefore it provides a channel, a pathway for you to check various theories of the electromotive force in at least this particular limit. And we will come to that perhaps during this conference in connection with applications like the test field method. There are a number of other effects which don't have to do with the electromotive force, they have to do with the Reynolds stress or the Maxwell stress. And again, they have contributions from the mean magnetic field and the mean velocity field. There are the effects known as the Arca effect. Uri Frisch here in the audience has worked on that in '87. And there's a number of other effects, including the lambda effect, which is proportional to the local angular velocity in a rotating frame. So it's the multiplicity of these various effects which motivate this meeting. Many of the people of the early years are still around, and I would like to mention Gene Parker and Paul Roberts. Gene was important in developing the concept of what is known as cyclonic events. And these are important to close the dynamo cycle to produce poloidal magnetic fields from toroidal magnetic fields that in turn are being produced by the differential rotation. And it is this effect that embodies the alpha effect that we are talking today and about during this week. Paul Roberts was important in a number of different fields, but let me emphasize what is important in dynamo theory. In particular, he developed a concise formalism of the Herzenberg dynamo in the way as it is nowadays introduced in books. He also produced the first fairly complete surveys of alpha effect dynamos in spheres, full spheres, or spherical shells. And most of all, he was important in translating the works of the people from Jena or Potsdam into English in this booklet or this technical report, which carries the name The Turbulent Dynamo, a translation of a series of papers by Fritz Krause, Karl-Heinz Redler, and Max Steenberg. Paul was also important in enabling the east-west connection. This was a time which was very different from nowadays, where it was difficult or even impossible for scientists of the East to either receive all the journals from the West or to communicate with the other scientists in the West. And it's because of this that it was such an important development, and it's also such a great honor to have Paul with us here today. You may remember that Paul and Fritz Krause had also interesting collaborations in the early 70s about the strength of fluctuations of the magnetic field, for example. Talking about the people of the early years, I must mention a few other names that are not here, in particular Keith Moffat, Sascha Rusmaiki, Michael Stix, and Günter Rüdiger. All not here, unfortunately, but I have been in touch with them, and they're all aware of this meeting and wish us the best of all. So let me now say a few words about Fritz Krause. The idea is that I was wanting to ring up Fritz Krause. And of course the reason for that is that I had the pleasure to work with Fritz during the early years, when I was starting my research career in between '86 and 1990. I worked with both Fritz and Karl-Heinz during those years because they were able not to visit West Germany, but they were able to visit Finland. And I, being from West Germany, did my PhD in Finland, and so it was a great opportunity for me to get in touch with them and to work with them. Which, by the way, was of course completely forbidden. It was not allowed for an East German physicist to work with a West German physicist. But given that I'm not in West Germany, but in Finland, this was not regarded as an obvious problem. I must also mention my PhD supervisor at the time was Ilkka Tuominen, and unfortunately he can also not be with us here today. It is unfortunate that Fritz really stopped his scientific activities essentially since '92, just after he ran successfully the IAU Symposium 157 in Potsdam, where many of us were still around. This was a time when, at the same time, the Isaac Newton Institute held a program on dynamo theory, where, again, many of us were there. So I have, and Fritz Krause was at that program too. So I have very fond memories of this particular time when Fritz was around and still active in research. But there are many circumstances that prevented Fritz now from coming here. Walking is not so good, he doesn't hear so well, and he doesn't see what is really written. And his wife also had a little accident, so that meant it was not possible to have her help in coming here. But I wanted to say a bit more about this story, because it is also an opportunity for us, or this meeting is an opportunity for us to reflect on a few past accomplishments and to think about what it is like doing research well into one's retirement age. I'm speaking as a youngster here, and I hope that many people will, or some of you will put me straight on this. But I should, or want to say that I did call Fritz Krause in November, and he was immediately, I mean, it was great talking to him again, and I told him, I tried to convince him to come here, but of course that was not possible. But he was agreeing to have a phone call with him, that I would call him up publicly. He was happy to doing that, but he did already back then say that he does not actually want to give any serious speech. He just want to greet a few people here. And I think it's interesting what he commented then, because he did say, he made a remark about Gustav Heinemann, who was an important German politician, and he was also the president of the Federal Republic of Germany between '69 and '74. And he is very well known for his over 2,500 public speeches, many of which are recorded. And so Fritz Krause explained me this story. Many people noted in his later years that his speeches were no longer that great. And even later still, Gustav Heinemann noticed himself, so according to Fritz Krause, that his speeches were not so great anymore. And I think it is in this spirit that Fritz declined to talking to us today. But of course, another reason for that is that he really got a little bit out of touch by having really stopped research since '92. By this I don't want to imply by any means that as one gets older, one is no longer as attractive as one was in one's younger years. And of course, this is evidenced by, for example, the great speech or colloquium that Jean Parker gave just the other day here at Albanova, and of course by the productive collaboration that I maintain with Karl-Heinz these days, and of course by the ongoing collaboration between Paul and Andrew Sauer. And there are many other such examples. But the younger generation among us very much look up to the important accomplishments of the grand old men of dynamo theories of those years. And so, in this spirit, it is important to have this meeting and to have you guys here, even though that was a bit of a challenge. But I'm glad that you all came. But yesterday, it was only since yesterday that Fritz called me and really said he doesn't want to speak us in public. And of course, I accept his request. And I can only guess upon the true reasons for doing so. And I elaborated a little bit on this with my Gustav Heinemann connection. But I was glad that Paul was able to talk to Fritz just a few minutes ago. And but I think the reason why Fritz didn't want to talk to us in public is, as illustrated by the the Heinemann story, is really that he doesn't want to compare himself with how he was when he was younger. So this brings me, or reminds me, of another connection, which I saw a documentary about Jean Sibelius just the other day. That was quite interesting in this connection. Jean Sibelius was an important Finnish composer, died in 1957 at the age of 92. Remember, he wrote his 7th symphony in 1924, at the age of 59. In the following years, he was not inactive. He was working on his 8th symphony. And after 20 years of trying, he finally burned everything he has done on that, according to the accounts of his wife, Aino. So this is how things can be. I mean, you really have very high standards, and of course, things change over the years, and people are just different. People like Fritz really don't want to do that, whereas other people continue, and it is very much of interest to all of us, as I said already, especially for the younger generation, to hear from how it was in the early days of dynamo theory, because it is very interesting in its own right. I think it is important that I accept Fritz's decision not to talk to us today, but it is also a lesson for me to restrain myself from knowing what I should and should not expect from others. And in this connection, I also would like to apologize to Paul, because I think I put quite a burden on him by asking him to talk to us today about the early days of dynamo theory, or the translation of the alpha effect to the West. The connection is obvious by now. I would like to apologize, because it was certainly not an easy thing for Paul to do, to accept such an invitation, especially because I came up with this idea only, or Igor and I came up with this idea, Igor Rogachevsky, and I came up with this idea only shortly before Paul came. And then Paul looked into his office, and at first he said no, but then he looked into his office and found some interesting material that will now support his talk. But I hope you can accept my apologies, Paul, and I wish to note that Paul just spoke with Fritz on the phone. I said this already, and I would therefore like to ask you what he said and what you think about his 2 reasons for not coming. And then, of course, for what it was like to get exposed to the developments in East Germany at the time. So, Paul Roberts, please.
Well, it's nice to be invited here, and in fact I'm very keen to come here because of the early association I had with Karl Heinz and Fritz Krause. I came to, well, it's a long story really. I learned something about the alpha effect before I went to East Germany, and I thought, what better thing can you do than to go to the horse's mouth, as they say in English, go to people who had invented the term alpha effect and had worked so hard developing this effect. So I think it was 1969, before most of you were born, I suppose. I went to Potsdam. I was very nicely received by the scientists there, particularly Karl Heinz and Fritz Krause. And they taught me all they knew at the time about these subjects. And I went back to Britain very excited about this. And we ran a NATO conference about this time in Newcastle upon Tyne. And these developments featured in this. This was actually long before it was well known in Britain. I think it's true to say that Keith Moffat hadn't really got into the subject well at that time. Although Keith Moffat invented the phrase helicity, there was a German word I picked up when I was in Potsdam, Schraubensinn, about the same property as helicity. And shortly after that, I went to an NCAR program in Boulder, Colorado. NCAR stands for National Center for Atmospheric Research. And I went there determined to continue the work that Fritz Krause and Karl-Heinz Redler had introduced me to. I did some new integrations of the dynamo models, and it was a very exciting time. And as Axel said, while I was there, another person on a different program in Boulder. Boulder is a city full of scientific programs. And NCAR was only one of these programs. But Michael Stix was there, and we found our common interests. We wrote some papers together. But then I thought, we should translate these papers from Potsdam. Now, I was incapable of translating these things. My knowledge of German was inadequate. But I think Michael Stix at that time, although very good at English, was still not really fluent in English. And so it was a perfect collaboration. I did most of the donkey work, and he went to, he got a microphone and spoke into it, recorded what he thought the translations were, and then we hammered out a text in English. And as the translations went on, Michael Stix's English got better and better, and by the end he was doing virtually perfect translations into a microphone, and I was slogging away, getting them typed up, and etc. And we produced this report that Axel mentioned. This became a very popular report, actually. It was quite soon sold out with NCAR, and if you're interested, they've reissued it now. Perhaps you know this, but it's now available on the web. And I still think it's got something going for it. Of course, it's badly outdated now. It's nothing like as useful as it was all those time ago. But even so, I think there's a lot of worthwhile things in it. I like to think so. So, nice now to talk to Fritz Krause again. It brought back to me the happy memories I had. Even though at that time it was a very restricted society, as Axel said, the people living in East Germany had very little freedoms. At one stage, I wanted to get my bassoon repaired. My bassoon had been made in the German Democratic Republic, far in the south, and Fritz Krause kindly got permission. He had to get special permission to go to this part of Germany, which is a long way away from Potsdam, and he drove me down there to get my bassoon repaired. It was an interesting trip. One of the interesting things was one felt that he was being kept track of, we could say that, while he was doing this journey to south of East Germany and back again. But that was an example of the kindness that I received from Fritz Krauser and Karl-Heinz while I visited Germany. I actually visited on several occasions. In the end, I was very ashamed that I hadn't learnt any German, because if I'd known at the start that I would be visiting so many times, I would have made an effort to learn some more German. But you know, as in Britain, languages are not, well, in my generation, languages were not pressed as they are now. And so I never really got exposed to it. At any rate, it was nice to speak to Fritz. It brought back happy memories of my time there. He sounded better than I expected. I couldn't really understand why he was not coming here. As Axel said, everybody knows what he's done, and everybody respects his work. But I think one of the things is that he is not so fluent in English now, as he wasn't so fluent as Karl-Heinz, even when I visited. And now I think his English is lack of practice, I suppose. Practice like anything else. And now on the phone, he was obviously searching for words that he once knew, and I think this is one of the reasons why he didn't feel he would want to come to this meeting. But he sounded very upbeat, as they say in America. Very, yes, I was very encouraged by talking to him and hearing how well he was doing. Of course, I asked him how his flowers are. He's a great cultivator of orchids. He said his flowers were doing very well. So, yes, it was a very enjoyable experience talking to him, and I'm sorry that the rest of you didn't get the opportunity to talk to him as I did. Well, I'm supposed to give a talk about this translation of the alphabet to the West. The thing about this that I didn't really know what to do was I thought it would be more interesting for the younger people to hear about the growth of hydrodynamics in the West generally. I mean, I didn't know when I started my research that I was going to hydrodynamics. I had no idea. I went to my advisor. You think I'd finished my undergraduate degree. I went to find a research supervisor. I approached Bondi. Now, Bondi was the extraordinarily impressive lecturer that we'd received as a student. So naturally I went to him. He said, well, I don't have a problem at the moment. And so I was very disappointed. I wanted something in relativity and cosmology, because he delivered brilliant lectures on this. But then he said, well, there's this thing about dynamo theory. He said, you know, there's this conjecture that a fluid can generate a magnetic field. I don't think I believe it particularly. But what's desperately needed is either an example of this, or maybe a proof that it's impossible. So that's the way I started my research, trying to essentially prove that dynamos couldn't possibly exist. And it was all because of Cowley. I never got a picture of Cowley here. I can operate this thing. How do I do that? Oh, that's our picture. Yes, there's Cowley. Now, I like this picture of Cowley. Cowley had this nice smile on his face, you know. But it wasn't really like that. I think he was smiling because of the difficulty he anticipated for anybody who followed his theorem of 1933. You see, he proved in 1933 that axisymmetric dynamos were impossible. And he anticipated I think he anticipated that generally it would be impossible, but he was certainly amused by the idea that people would be struggling with this problem as they were for a number of years afterwards. And, well, Caroling did this work in 1933, and you could say this was the beginning of MHD in some sense. How does one define MHD? When did MHD start? Yeah, this is a good question. There was several things that have been fields that predated the discovery of magnetohydrodynamics. There was, for example, the experiments of Hartmann and Lazarus in 1937, famous experiments. And as I said, it's Caroling in 1933. There was the law of iso-rotation by Ferraro, which was, I think, 1939 maybe. But I don't think this marks the beginning of magnetohydrodynamics. I think the beginning of magnetohydrodynamics really must be dated to Alfvén, because he was the man who first of all demonstrated wave motion. And it's remarkable, really, that this idea that wave motion could carry energy efficiently to large distances that started MHD as I see it. I met Alfvén first of all at this meeting in Salzburg in 1957, I think it was. I've made a note of some of these dates because I never remember dates. There was an IAU symposium, 1956 at Salzburg. Several people there I met for the first time, including Caroling. Caroling was, I met him at an embassy party. He was a great damper on the proceedings because the embassy party was one in which everybody from Britain who was in Stockholm at the time was going to celebrate a release from the labours of the day. And Caroling sat there, not drinking alcohol at all, and looking at everybody else, I thought, with displeasure. Be that as it may, he was Caroling was a man who was very self-critical and very critical of other people. And I also think it's amusing in the way that he published this Caroling's anti-dynamo theorem, and his proof has a hole in it. And he obviously didn't extend his criticism to that. At any rate, under Alfvén, a vigorous program started of experimentation and theory. Lundquist wrote a famous review, Lundquist was one who wrote a famous review, and Lehnert did some famous experiments using liquid sodium. And previously, Lehnert had tried to do these experiments, and it's explained on this view graph what these experiments were. There was a column of fluid, conducting fluid, and then it twisted at the bottom. It transmitted a torsional wave upwards. And then by looking at resonance between the frequency and the height of the column, you could get evidence of Alfvén wave propagation. And this was probably the best you could do at that time. It's obviously exciting to do these because liquid sodium is not an easy fluid to use. And as it says on this typical understatement, Lehnert says the practical details of sodium experiment were not without problems. He explained of his problems. His apparatus leaked, sodium went out in the environment, it caught fire, and the institute was pervaded by smoke for the place basement, and later on he had to dispose of contaminated sodium. So he took it in a tin, about a litre of it, and threw it into the bowl. As he said, it would burst like that of a medium heavy artillery shell. It rattled the windows, and motorboats in the vicinity beat a hasty retreat. At any rate, he was apprehended by the police, who took a dim view of this, and he could only survive without a fine by giving them an impromptu lesson on MHT. Well, anyway, I talked about, yes, I went to the United States and had a profitable time working with Chandrasekhar, who was also deeply interested in dynamos, although he didn't succeed in doing anything very impressive in this area. But he had a similar view to Cowley as me. He always referred to the frozen flux theorem as Alfvén's first theorem. So eventually I asked him, well, what is Alfvén's second theorem? That's a good question. And he said, well, I don't know if I put it on the next one or not, here's his second theorem. This is typical Chandrasekhar humour in a way, deeply sense of humour. But obviously he had suffered too from Cowling's severely high critical faculty. Anyway, I'm talking too long. Let me go on to say, at that time, the main advances in dynamo theory were probably being made by Teddy Bullard. He was from a famous brewing family. If you go to East Anglia, you may still see signs of Bullard's ales. And he was a prominent Cambridge physicist. He intended to be an experimentalist, but he went into Rutherford's lab and made some mistake. And Rutherford said, never darken the doors of my laboratory again. So he left and went into theoretical physics and experimental studies in oceanography, but not in Rutherford's laboratory. He was a wonderful man, actually. Bullard. He was so sympathetic to research students like me. They had me to his home and staying in his home and discussing his problems with the dynamos. But this is Alsacer, who was the other main figure at that time. Walter Alsacer was, well, of course, Eugene Parker knew him very well. He was at Salt Lake City at that time, University of Utah. But when this was taken, it was later, it was in, I think, Johns Hopkins University. And the nice thing about this slide is you can see the blackboard. You can see what it was talking about. Dynamo, it says, generator, Babcock, referring to vectors and stars. What does do? Oh, 20, yeah. Oh, yeah. Yeah. Thank you. Well, actually most of these studies were purely kinematic. Very little dynamics came into either Bullard stuff or, for that matter, the Alsacer stuff. But Alsacer did one very useful thing. He pointed out that in a rotating system, the natural unit for magnetic fields was this one, the scaling. Now in the scaling, U is magnetic permeability, rho is density, eta is defined here, that's magnetic here is the rotation rate. If you work that out for the Earth, that's about 12 Gauss. But after that, I introduced the Alsace number. This is based on the same scaling, and that now plays quite an important role, at least in geomagnetism, in deciding the scale of the field that you're looking at. So after that, I should. Well, I've all seen him. He's been around here a lot. And he started, in a way, he started the alpha effect, as Axel mentioned. He did this. Well, he came to talk to us about it at Yerkes Observatory when I was there as a postdoc. He was interested in the effect of cyclonic turbulence and predicted that it would produce a generation effect, a gamma effect. Actually, gamma played the role of alpha, but it's a better name because gamma starts with a G, and G means generation. It was a right simple to use, I think. Alpha means nothing in this connection. I mean, in a sense, it's an absurd choice. But he started alpha omega dynamos and produced a beautiful example of what is now a solar cycle. It was then called a dynamo wave. I mean, I was foolish. I should be jumping on this too. When you're young, you make mistakes all the time, and I made a mistake of not taking this seriously enough. I mean, my attitude was, here's this man, he's produced an equation. Well, I couldn't solve the original dynamo equations. They were too difficult. But now he's produced another equation, which is nearly as difficult to solve. You think of the computers at the time, they were really very primitive. So I said to myself, you know, okay, he's got another equation. It hasn't got to the firm foundation as the original electrodynamic equation. Why should I work on it? Of course, now you can see that that was a great mistake. I should have spent time on it. But there we are, foolishness of youth. After that, the next development that interested me particularly was Stanislav Baginski. Now, Stanislav Baginski was really a plasma physicist who had become a geomagnetic expert. And he produced what I suppose was the first rigorous proof, mathematical proof, of the alpha effect, or rather, the alpha effect, for alpha omega dynamos. A real tour de force. I came across it because I met Bullard at some luncheon or other. He said, Roberts, he said, have you looked at this fantastic claim of this Russian? I mean, he said, you should look at it. So I went away and looked at it, and you know Russian papers, they're so condensed, and this was the most condensed I'd ever seen. It was, you had to look at every word, essentially. And of course, word meant translation. So even the words were probably not as good as the Russian original. And so it was a real hard work. And I couldn't believe how somebody could go through this lengthy analysis and have the persistence to get to the end of it. Because you look at it sometime, it's a fantastic paper in a way, and he proved the alpha effect rigorously, really. Well, some mathematicians still demand more rigor, but I think it was rigorous. So, after that was the thing we talked about earlier on. This was here was the trio of Steinbeck, Kaiser, Redler, and there was a fourth person on this picture. I had to get it eliminated. The director of the institute at Potsdam liked to get his photograph taken, and I was with my camera there trying to get a picture of these three, and he would always pop in to the left or the right, this trader. So there's a blank space here where he'd been eliminated. So this was the, well, I've already said enough about this already. This was a very important phase of my scientific life, and these were the men responsible. I thought Stegbeck was quite an impressive personality. I didn't see so much of him because he was so active in the East German Academy, and he was based in Berlin, so I didn't see much of him, but I got the impression he was a pretty smart motivator of a lot of the work that went on in the trio. So I think I'm more or less got to the end of this, and that was the book that translation that we produced, and this was what I mentioned, a very popular translation, and perhaps this is what the organisers meant when they said I should give this lecture on the translation of the album effect to the West. Thank you very much.
Thank you, Paul. You have time for questions, please. Paul, you mentioned that the Cowling theorem had a hole.
Yes.
And since when was that actually discovered, and when was it patched?
Well, I don't think I think I was the one to discover it. And there's no doubt it seems right in my opinion. In fact, there are other proofs now that show that it's right. But Cowling's proof was not perfect. And well, I don't think I'll go into it now, but what I don't think I'll go into it, but there is a hole in it. He takes a little loop integral around, you remember this thing, and then at some stage he has to cancel out the average B around the loop with the maximum B on the cross section of the little area which is as this loop as the circumference. And at that stage he blithely cancels them out. But if you look at what's involved with the cancelling out, it's not so obvious. I got Stephen Childress interested in it. Now he's much more mathematician than I am. Steve Childress looked at it for an hour with me. He said he didn't see how to fix it. But I'm sure some clever mathematician can fix it. Just I'm not clever enough to do it. It's certainly not obvious.
That is remarkable. Other questions, please.
You said that Braginsky predicted alpha effect on this equation?
Oh yes, he was an alpha effect. He didn't do anything like an alpha squared dynamo. He had a dynamo which was dominated by the toroidal field, and then the toroidal field essentially came into existence as a diffusion effect on top of that. So the dynamo is merely a perfect conductor, but this last diffusion effect, creating toroidal field, makes it it makes it generate, and also is an alpha effect. It's a genuine alpha effect. I mean, Andrew Sauer's a great expert on this. Maybe Andrew Sauer will talk about it, but he did a very famous paper on Braginsky's method in 1972, where he produced a kind of rational way of doing this, not this massive calculation that Braginsky had done. Andrew had a more efficient way of doing it. So it's one that where you have to think in sort of quasi-Lagrangian terms. This is a natural way because the thing is almost like perfect conductor, except for the third term of the expansion.
Any other questions, please?
I think I've floored everybody.
Braginsky doesn't relate it alpha effect with helicity.
No, he didn't, but Andrew did that.
Yeah,
Andrew,
it is.
well, in a way, it comes in a generation term, but
you're being persistent about this. Basically, you've got your azimuthal field going around in a loop. Then you have wave motions on top of that. So you can think of the zonal flow and shearing creating the azimuthal field. Now what the wave motion does is start to distort that field line. Think of it still frozen. It's still frozen when its waves are acting. Now you've got a distorted field going around. That distorted field starts to diffuse, and it produces a meridional component of field, which has a non-zero average. Well, the wave has to be sufficiently complicated for it to do it. But then you've got this distorted field line, which then diffuses. There's three orders involved. You have the lowest order, you have the azimuthal flow. At next order, you have the waves. And then an order lower, you have a mechanism for generating a meridional field. And that's where the alpha effect comes. That's the process of producing a current in the zonal direction, which is producing this meridional field. So it's a slightly subtle effect, but it's an alpha effect, all right.
That was 64, right? This
Yes.
original paper. That was fairly early on. So the connection between his 64 paper and, for example, Gene Parker's 55 paper, and later on other papers, when was that connection actually being drawn? When was Roginski really discovered? What do you recollect of that?
Roginski knew about Parker's paper, certainly.
Yeah.
He knew about the East German.
He used gamma as well.
He used gamma as well, yeah. Yeah. Another question there.
Another question?
Well, I don't have a question. I just want this a kind of confirmation. After the translation was published, and maybe even a little bit before, because some of us, certainly myself, we did understand German, there was quite an excitement in the group around Avery Schatzmann at the Institut d'Astrophysique in Paris, and we were all busy. I don't remember, it must have been 67 or so. I had just returned from the Courant Institute, and we were all busy studying this thing and trying to understand what it means, etc. So that, and we're talking about people who were not primarily fluid dynamicists at that time, but astrophysicists.
And most of them, with the exception of Schatzmann, were very young.
Thanks, Uriel. Any other remarks? Maybe Gene, what were you thinking about the response among the community? Maybe you come to that in your talk, but if you have any comments on the alpha effect here at this point.
After a few years, people began to get interested in the dynamo, and things began to progress. And as Paul has mentioned, we had Roginski's remarkable paper, and I much prefer Sauer's rephrasing of that. It's much easier for a mortal like myself to read it and understand it. And then, of course, the Steenbeck, Krause, and Radler reformulating the kinematic dynamo in using a quasi-linear approximation, I guess I would call it, which then gives you a systematic way of proceeding to develop the mathematics. I use that short sudden approximation, where in negligible time you deform the field and then you hold it and let the steady and then let the diffusion blur everything, get rid of the high energy, the high wave number components, which is an easy way to demonstrate the principle, but it doesn't give you a way of connecting up to real dynamics very well. So the quasi-linear approximation was a big step forward, giving things in terms of velocity correlations and so forth that you normally use in turbulence. So I was doing other things, but I was very pleased to see there was slow and steady progress on it.
Could I ask whether that short Saturn approximation you mentioned reminds me very strongly of the Bacchus dynamo, because he used the same device.
Yeah, he used exactly, he wrote it down formally, and worked it out. Well, I guess a mathematician would say worked it out properly.
Yeah, that's right.
I stated it and figured it was obvious from there on, and didn't do any more.
So did you have connection, because he was on campus all the time, wasn't he? Did you get connection?
He did not work on this while he was at the University of Chicago. This was a later development. He had gone out to the West Coast by then.
He went to Yankees when I was there for a year and worked with Chandrasekhar, and he was very interested in dynamos then.
Yeah.
I just wondered if he picked it up, the short sudden approximation from interaction with you.
Well, he might have. I don't know. That's the way I always expressed it.
Thank you, Gene. And Ulrich Frisch has some more remarks on this issue. Please, Ulrich.
Yes, this is not a historical remark, really. There was a bit of confusion in the first few years after the introduction of the alpha effect, because people hadn't quite realized something that is well known now by scientists who do so-called homogenization, which is a horrible word, namely finding the macroscopic properties of material which on smaller, say, mesoscopic scales have such and such spatial variation. For example, if you have a rod in which the heat conductivity varies periodically, as you know very well, on scales larger than the wavelengths of this thing, you have an effective diffusivity, which is just a harmonic mean. If you are in more than one dimension, for example, you can also easily show that a plate now, not a rod, which has a, say, biperiodically varying diffusivity, has an effective, now perhaps anisotropic diffusivity, which you cannot calculate by hand in general. You can prove that it exists, you can show that it is the solution of a certain well-defined auxiliary problem, but obtaining it in explicit form is generally not possible. And there is the confusion I was referring to in the birth, the alpha effect, is that there are actually two different issues. One is to show that material, now fluids, having a certain property, later it was identified to be the lack of parity in variance, which is slightly more general than helicity. That such fluids on large scales, one can easily show that they satisfy alpha-type equation, but the values of the corresponding coefficient or coefficients are solution of auxiliary problem, but one cannot necessarily solve. There are actually two kind of perturbation theories here. One is a multi-scale perturbation theory that allows you to extract the large-scale behavior with certain coefficients which are solution of auxiliary problem. And if you are very lucky, these auxiliary problems can themselves be solved perturbatively if you have a suitable small parameter, which now cannot be the scale separation because you've already used it. It can be a short correlation time or something of this kind. And the inability in general to solve explicitly, analytically, the second stage, in the first few years was a source of slight distress until people moved to this thing. But actually the situation is very general, and now we can go back to Hilbert and Chapman and Ensel, who showed that if you have a microscopic fluid in which the local thermodynamic characteristics like the density, the mean velocity, the temperature vary slowly, then you can extract equation, namely the hydrodynamic equation for the large-scale behavior. But the value of the transport coefficients cannot, in general, be obtained in closed analytic form. There are some exceptions that Maxwell already discovered, but one has to be aware of this in rethinking the history of the alpha effect, that in the early years, these two stages were not well separated in people's approaches.
But you're probably not saying that in the absence of a small parameter or in the absence of scale separation, the case is hopeless, because you can still treat various ways of mean field theory numerically, at least, if not even analytically. Yes. Does anybody want to respond to this? Nathan.
What is true? That's what happened with mean field theory, very similar to the situation with molecular physics. But I would like to say that scale separation, of course, important thing. But nevertheless, in meteorology, in oceanology, they use mean field theory without any scale separation very successfully. Because from fractal point of view, very difficult to find system with good scale separation.
No, but I mean, look, there is, I couldn't agree more with what you say without having to mention the alpha effect. Just take the modeling of realistic inhomogeneous turbulence as used by engineers.
Mm-hmm.
They were using concepts such as mixing lengths, eddy viscosity, etc. Was reasonable, some people would say, with great success, and there are some names, even Kolmogorov and Karman are attached to. And they use them, of course, in almost all instances without having the required scale separation that makes it mathematically rigorous.
Of course, mathematically not rigorous, but as is very often happens in physics, we have good theoretical problem, but nevertheless, this tool is enough to it further. Second, of course, scale separation gives you possibility to find all, to prove all these concepts in a rigorous way. It's true. And after that, just experiment, let's say, is it true or not true to use in situation without scale separation.
Thank you, Nathan, and thank you, Uriel, and thanks, Paul, in particular, for this very first and interesting session. We have now coffee and lunch. We have at 12:30 upstairs in the 23rd floor. So thanks again, Paul.